I'm sure you've heard the news by now. It started as a whisper in astronomical circles, then became a roar that echoed across the globe. A strange cosmic ping, a signal from the deep dark. In the quiet hum of an observatory, under a canopy of stars, our electronic ears were listening. These colossal dishes, our radio telescopes, are designed to capture the faintest murmurs of the universe. But what they found was not a murmur, it was a shout. Almost as soon as the initial data was processed, the internet ignited. Social feeds exploded with theories, each more sensational than the last. Was this it? The moment we'd all been waiting for? The acronym SETI, the search for extraterrestrial intelligence, was on everyone's lips. Speculation ran wild. Perhaps it was an alien probe, a lonely sentinel finally making its presence known across the void. Or maybe, just maybe, it was the prelude to dramatic contact, a deliberate message sent from a distant civilization. The story was irresistible, a perfect blend of scientific mystery and science fiction fantasy. But in science, the most exciting stories are often the ones that require the most scrutiny. So let's cut through the hype and look at what the data actually tells us. What are the raw characteristics of this enigmatic signal? First, it's loud. In radio astronomy, loud doesn't mean you can hear it with your ears. It refers to the signal's intensity, its power. This ping was exceptionally bright, standing out starkly against the faint, constant hiss of the cosmic microwave background radiation. It was a flare in the darkness. Second, it's brief, incredibly brief. The entire event lasted for just a few milliseconds, a thousandth of a second. It's a cosmic flashbulb, gone almost before you know it's there. Capturing such a fleeting event is a monumental technical achievement in itself. And third, the most intriguing characteristic of all, it's weirdly regular. The signal isn't just a one-off event. It repeats, not randomly, but with a discernible, almost clockwork-like pattern. This regularity is what truly sets it apart and fuels the most intense speculation. When astronomers see a signal that is loud, brief, and regular, it doesn't immediately scream aliens. Instead, it screams fast radio burst. FRBs are one of the most fascinating mysteries in modern astrophysics. They are intense, millisecond-long bursts of radio waves originating from deep space. Some are one-off events, cataclysms that happen once and are never seen again. Others, like this one, are repeaters, flashing over and over from the same spot in the sky. The leading theory is that many FRBs are caused by magnetars, a type of neutron star with an unbelievably powerful magnetic field, trillions of times stronger than Earth's. A starquake on its surface could release a colossal amount of energy, seen by us as a fast radio burst. Or it could be a repeating pulsar signal. Pulsars are another type of neutron star, the collapsed cores of massive stars. They are famous for their extreme density and rapid rotation. As they spin, they emit beams of radiation from their magnetic poles. If one of these beams sweeps across Earth, our telescopes detect a pulse. They are the universe's lighthouses, and their regularity is so precise that they can rival atomic clocks. So, a repeating FRB from a magnetar or a signal from a pulsar are both powerful, natural explanations that fit the evidence. They are not necessarily proof of extraterrestrial intelligence. But before we even look to the stars, we must first look much, much closer to home. The universe of radio signals is crowded. Our radio telescopes are exquisitely sensitive, but that means they also pick up human-made interference. Thousands of satellites orbit our planet, broadcasting signals for GPS, communications, and television. A stray signal from a passing satellite can easily be mistaken for a cosmic event if not carefully vetted. It's not just what's in orbit. Telescopes also pick up human-made interference from ground gear. This is called radio frequency interference, or RFI. It can come from anything with an unshielded circuit: a cell phone, a car's ignition system, a faulty microwave oven in the observatory's kitchen. In fact, a famous series of signals called perytons baffled astronomers for years until they were traced to scientists opening a microwave before it had finished its cycle, And it's not just our technology. Earth itself can play tricks. Telescopes also pick up ionosphere quirks that bend radio waves. The ionosphere is a layer of our upper atmosphere filled with charged particles. Changes in this layer, caused by solar activity, can distort or reflect radio signals from space, or even terrestrial signals, creating strange and misleading effects. So how do scientists separate a genuine cosmic whisper from all this noise? They follow a rigorous process of verification. First, scientists triangulate. By using multiple telescopes located hundreds or thousands of kilometers apart, they can pinpoint the signal's origin in the sky. If all telescopes detect the signal at slightly different times, they can trace it back to a single point in deep space. If it's detected by only one, it's likely local interference. Next, scientists repeat observations. They point their telescopes back to that exact spot in the sky again and again, waiting for the signal to reappear. A genuine astrophysical source, especially a repeating one, should show up consistently in the same location with similar characteristics. And crucially, scientists rule out tech glitches before saying anything bold. They run diagnostics on every piece of equipment. They check logs, cross-reference with other observatories, and analyze the signal's properties to see if it matches any known signature of man-made RFI. This is the unglamorous, painstaking work that forms the bedrock of discovery. History is filled with examples of this process. In 1967, Jocelyn Bell Burnell detected a perfectly regular signal, repeating every 1.33 seconds. It was so clock-like they nicknamed it LGM-1 for Little Green Men. But through careful observation, they determined it was a natural phenomenon, the first ever discovery of a pulsar. It was a revolutionary finding, born from ruling out the extraordinary in favor of the verifiable. More recently, the first repeating fast radio burst, FRB 121102, was traced to a dwarf galaxy 3 billion light-years away. It took years of follow-up observations with some of the world's most powerful telescopes to pinpoint its home, confirming that these events are truly extragalactic and immensely powerful. The investigation into this new signal is happening right now, on a global scale. The era of the lone astronomer is over. Today, vast arrays of telescopes work in unison, like the Very Large Array in New Mexico or the Future Square Kilometer Array. They combine their data to create a virtual telescope the size of a continent, giving us unprecedented resolution. Researchers are also conducting multi-wavelength follow-ups. They're pointing not just radio telescopes, but optical, X-ray, and gamma-ray observatories at the source. If a magnetar is responsible, we might see a corresponding flare in other parts of the electromagnetic spectrum. This holistic approach is key to solving the puzzle. Behind the scenes, supercomputers are crunching petabytes of data, using machine learning algorithms to search for patterns and filter out interference. Much of this data is made public, allowing citizen scientists and researchers worldwide to join the hunt, bringing fresh eyes to the problem. So, for now, what we have is an amazing mystery. It's a puzzle with several plausible, natural solutions, each of them fascinating in its own right. The possibility of an artificial origin, however remote, serves as a powerful motivator, pushing us to look harder and be more rigorous. This is the nature of ongoing research. It's not about instant answers, but about a patient, methodical process of elimination. Every hypothesis, from the mundane to the extraordinary, must be tested against the cold, hard facts. This signal is a profound reminder that the universe is constantly throwing surprises our way. It's a place of violent, energetic, and bizarre phenomena that challenge our understanding of physics. But in the end, evidence wins over excitement. The scientific method, slow and steady, is our most reliable guide through the cosmic unknown. So, embrace the wonder, but also embrace the skepticism. The truth is out there, written in the language of data and physics, waiting to be deciphered. Stay curious.